Here's the situation. We were supposed to have exam 3 on chapter 7 and 8. Now, today. No students in the classroom. 3 have contacted me. They're flooded out. They can't get through. The other 2, no word. So since there's nobody here, I'm going to go ahead with the lecture on the next section. Exam 4. We'll start with chapter 9. And if there's time, I'm going to do chapter 10 today also, or as far as I can get. All right. Chemical reactions. You're probably wondering, why is this chapter so late in the book? Haven't we been talking about chemical reactions up to now? Well, yes, in a way we have, but we're going to get into more detail, down into the weeds, as they say. So we're going to look at the different types of chemical reactions, classifications that will help you identify what you're dealing with when you think you see a chemical reaction, how to approach it. And then we're going to get into the specifics of balancing redox reactions, telling the difference and balancing those chemical reactions. We'll get a little bit of theory, right? And then we'll introduce, we'll skim across the surface of several topics. Thermochemistry, exothermic versus endothermic, reaction rates, equilibriums, and then Le Chatelier's principle. Now, of course, if you were here in person, you'd get hard copies of all the documents that I normally hand out. Plus, you'd get the next week's lab exercise, osmosis and dialysis. And then I also going to hand out the exercise after that, which is the following week, Le Chatelier's principle. So next week and the week after, we have 2 back-to-back labs. And that will be it. That'll be all the labs that we're going to do. Okay, so let's get started. All right, chemical reactions. We introduced the concept early on in the semester about identifying physical properties versus chemical properties and physical change versus chemical change. And the primary focus on determining whether you have a physical or a chemical process is identity. If the identity of a substance changes during the process, then that is a chemical reaction. Now, there are various ways you can identify a substance, right? Very often we rely heavily on reactivity. How does that substance react with something else? So there are different types of chemical reactions, and the way they're classified is not exclusive. One classification does not exclude another one. So you can have multiple classifications of the same reaction, depending on how you identify the substances and the changes they undergo. So let's see, I have slides here, I think, following up. We're going to look at these types: combination reaction, which is also a synthesis; decomposition, which is just the opposite of the synthesis; a single displacement reaction, double displacement reaction, and oxidation reductions. All right, for a combination reaction or a synthesis, we're generally looking at simple reactants producing something more complex. So a perfect example of that is an element makes a compound. Now, there are examples where you can have compound making another compound, but in that case, you would have to use up all of these and make the one. So it's simple to complex. It's easiest to understand as element plus element equals compound. That's the purest type of synthesis. Then if we have a decomposition, we just run it in reverse. Right? Just reverse the arrow. Or flip it around. You have a compound, makes elements. And the example there is copper 2 oxide decomposes into copper and oxygen gas. A displacement reaction or a single replacement has, let's see, we're going to put, here we have 2 parts to this compound and an element. And the element is going to replace one of these components. Well, when we write a compound, we usually, and it's an ionic compound, we usually write the cation first, anion second. So if this is a metal, in our example, the metal replaces the cation. So if that were true, now we would have Y out here by itself and X and Z. That's a single replacement. Sometimes these are oxidation reduction reactions, but since we haven't defined what that is yet, we'll save that definition till later. Just recognize that this reaction, anytime you have an element displacing another element in a compound, it's always an oxidation reduction reaction. Okay, a double replacement. A double replacement reaction, you have 2 compounds and they basically just swap partners, right? The cation from one goes to the anion of the other and vice versa. And here's a perfect example. Silver nitrate is completely soluble in aqueous solution. Sodium chloride, obviously, table salt, is soluble. And when the sodium and the silver swap places, silver combines with the chloride, sodium combines with the nitrate, and then you've got to see whether or not there's a precipitation, because usually there is. The precipitation in this type of reaction is what drives it. This drives the reaction toward products. Now, this is not always the case. I can think of examples where you would have a double replacement or exchange reaction where a precipitate is not formed. Okay, yeah, let me give you an example. One where a precipitate is not formed. So let's say we have an acid and a base in solution, and the hydrogen and the sodium swap places. Now, this is a special kind of exchange reaction or a double displacement called an acid-base neutralization. So when we do that swap, we get sodium chloride in aqueous solution, and we get water. The formation of water in this reaction drives the reaction to the right. All right, we'll talk about those a little more later. Actually, in chapter 10, we get into this acids and bases in more detail. A combustion reaction. A combustion reaction requires at least one factor, that is gaseous oxygen. You have to have oxygen in order to identify a combustion reaction. And this one is also an oxidation reduction reaction. So here in our example, we have propane, right? That's the same stuff you have in the tank that runs your barbecue grill, or that you use to heat your house or cook your food in some cases. And all you need is whatever the compound is plus oxygen. All right. Identify the following categories for this reaction. Okay, we have 4HNO3, correct? Yep. And it makes 4NO2 plus 2 water plus oxygen. Okay, so what does this look like? It looks like a decomposition, right? Right? More complex to less complex and more of them. Okay, so that's definitely a decomposition. All right, it can't be a replacement reaction of any kind because there's only one reactant. And decomposition is the only possibility, right? A combination or a synthesis is the opposite of decomposition, so you can't have both. So this decomposition is the only one that's of our multiple choice that's valid. So let's classify each of these. Let's see, we have, well, okay. I don't need to write it on the board, do I? A says magnesium metal is combined with hydrochloric acid, and it makes magnesium chloride plus hydrogen gas. Notice that you've got an element, a compound, and magnesium effectively replaces hydrogen. I mean, I better put them on the board. I can talk about them better. And that yields magnesium chloride in aqueous solution plus hydrogen gas. Okay, we need 2 of these. There we go. All right, so what's happening? This magnesium is replacing that hydrogen. This is a single replacement reaction. And ends up over here. It's also we haven't defined it yet, but it's also an oxidation reduction reaction. So I think they're probably just going to give you the first one. Yeah, displacement or a single replacement reaction. How about the second one? We have hydrogen chloride gas and ammonia gas. And that makes ammonium chloride solid. That is a synthesis reaction. We use this reaction to see if our fume hood is working. All we do is get concentrated hydrochloric acid in one beaker and ammonia in another beaker, and they vaporize. Right? They form vapor here, and they mix in the airstream and form this solid. Makes a fog. And you can see the fog getting swept into your fume hood, so you know it's working. Now, there are easier ways to do it, but it's fun to do it this way anyway. This is a synthesis reaction or a combination. How about C? Okay, we got ammonia again. This time we're combining oxygen and we're making nitrogen monoxide or nitric oxide, I think sometimes it's called, H2O. What have we done here? The key to focus on here is that oxygen. That's a combustion reaction. And it's also a redox reaction. Now, I've been identifying redox in here as an additional element, but I haven't defined it yet. So we need to do that. We need to define, what do we mean by oxidation reduction? All right, oxidation reduction. The best way to understand oxidation reduction is focus on the electrons. If you have two reactants, you can have more, but if you just have two, and electrons are transferred to some part, from some part of one reactant to some part of another reactant, that is a redox reaction. Now, what do we mean by oxidation and reduction? Well, the best way is to use this acronym. Oil rig. Oxidation is loss. And what we mean by there is oxidation is loss of an electron. If something is oxidized, it loses electrons. Loss of electron. Okay, reduction then would be gain of electrons. All right. Some reactions, many reactions actually, do not transfer electrons during the reaction. They are non-redox reactions. One of the clues that I was referencing before, say you have, let's do a combustion reaction. Let's get the combustion reaction we had before, which was, let me go back. Okay, 4, 5, 4, and 6, 4NO. Yeah, I think that's right. 6, 10, 10, 4 nitrogen, 12 hydrogen, 12 hydrogen. Okay. This we identified as a combustion reaction. But notice, if you have an element on one side of the arrow, it can be either reactants or products. In this case, it's on the reactant side because this is a combustion reaction. If you have an element here and it shows up in a compound on the other side, then that is guaranteed a redox reaction. So in order to determine whether electrons have been transferred, we need a bookkeeping scheme, some way to track the electrons. How many are here? How many are there? And then after the reaction, how many are with this element and how many were with that element? And did they change during the reaction? So to do that, we introduced this scheme called oxidation state or oxidation number. It'll be either plus or minus some whole number. And in some cases, it is actually the charge on the ion, but not always, because you can apply oxidation state to covalently bound compounds where there is no charge. That's why I call it a bookkeeping scheme, because it doesn't guarantee that you have a charge on any atom or any group of atoms. It's just a way of tracking the electrons. Okay. So let's get some, of course, we need some rules. And they're coming up next. Okay, rule number 1. The oxidation number of any element by itself in its most stable state at standard temperature and pressure is 0. So for instance, okay, this is the element rule. If you have an element here, say it's sodium metal, its oxidation state will be 0. And remember when we talked about the symbol for an element, right? It has 4 positions, 1, 2, 3, 4. And initially, I said that this position in the upper right-hand corner was reserved for charge. Well, now we're going to modify that a little bit, and that position now can be used to identify the oxidation state, not necessarily the charge. But in this case, it's true. There is no charge on that atom. All right? That's rule number 1. Rule number 2. If you have a monatomic ion, the oxidation state or the oxidation number is the charge. So if sodium were in a compound like sodium chloride, right? Maybe it's in a solution. This is going to have a +1 charge and -1 charge. So the oxidation number for sodium is +1. The oxidation number for chlorine or chloride ion is -1. Those are actual charges and oxidation numbers. Okay. Now we're going to look at group 1A and group 2A. Those are alkali metals. And alkaline earths. Okay. Now, what we're saying here is the oxidation number for those elements, if they are in compounds, right? If they're not compounds, if they're pure elements, then this is the rule. But if they're in compounds, then the alkali metals are always +1, and the alkaline earths are always +2. Now, I might add one, the 3A group. Boron, aluminum, and gallium, if they're in an ionic compound, right? The boron group, which doesn't have a special name, they would be +3. I know that's not on here, but I'm going to add it. The 4th one, hydrogen in a compound. When hydrogen is in a compound and it's the first element, compound first, it's a +1. Okay. Let me see if I've picked up the exceptions to the hydrogens. No. Okay, I'm going to add it here. If hydrogen is in a compound and it's second, that means it's with a metal. Right? So, for instance, if we had lithium hydride, the metal's first. Well, lithium is an alkali metal, so it has to be +1. That means if we're going to balance, and this is another rule coming up in a minute, if we're going to balance the oxidation numbers, hydrogen now has to be a -1. Okay, in those situations, just think of the compounds, any compound you can name with something hydride, it's a -1. Okay. Number 5. Oxidation number for oxygen in oxygen-containing compounds. So oxygen is a -2. If it's in a compound, oxygen's a -2 unless it's a peroxide. What's a peroxide? You have an oxygen, single bond to an oxygen, then you have something else. That's a peroxide right here. So both of these together are -2. So each one is -1. So the oxygen in a peroxide is -1. All right. Okay. Number 6. If you have a binary compound, and your authors typically mean 2 elements, but we can also use polyatomic ions here. But in a binary compound, the more electronegative element, if it's just 2 elements, the more electronegative element is assigned a negative oxidation number. And that's equal to its charge in the ionic compound. So what we're saying is that in a binary molecular compound that is covalently bound, then the more electronegative gets the negative oxidation number. I'm trying to think of an example. I've got an example, but it's already covered up here. If you have water like that, the more electronegative element is oxygen. So it gets the -2 and hydrogen gets the +1. And that's already covered in a previous, but 6 also reinforces that prospect because water is a covalently bound compound. Okay. 7. This is what you do with all your oxidation numbers. If you have several elements in a compound and each one has an oxidation number, you multiply the number of elements, the subscript, times that value, and then you add it to the others, adding them up the same way. And all the sum must be 0. Sum of oxidation numbers equals 0 for neutral compounds and equals the charge for polyatomic ions. Okay? All right, so let's take some examples and apply the rules. Okay, K2Cr2O7. We know how to name that compound. Potassium, right? It's a type 1 compound. Potassium dichromate. That's it. Okay. So for each of the elements, what would be we'll look through the rules, right? Alkali metal, it's a +1. Oxygen, it's a -2. Now we have to calculate what the chromium is. All right, so we add up what we've got so far. Right, 2 times +1 is +2, and 7 times -2 is -14. That would be -12. So in order to satisfy the summation rule, which in this case would be 0, we need a plus 12 right here. You have 2 chromiums, so each one of those chromiums contributes plus 6. Okay? And there's the evidence. How about the carbonate polyatomic ion? Has a charge. All right. Where do we start? Well, you start with the ones that are given values, right? In this case, oxygen. We don't have a rule for carbon, but we do for oxygen. In this case, the oxygen is -2 times 2 is -4 total, right? Okay. Well, if we're going to have, let's see, 2 times -2s. Oops, sorry. My mistake. I wrote carbon dioxide. This is 3. Okay, that's -2. This is -6 total. That means, we need 2 negatives not to be neutralized by the positives. So we really only need to balance -4 up here. That means +4 for carbon. Now, satisfy yourself that I'm correct. Sum them up. -2 times 3 is -6. And a +4 equals -2. So we did a good job. All right, let's look at this MnO2. It's a neutral ionic compound. Start with the oxygen, because we have a rule for oxygen. -2, so -4 total. And we need to neutralize all of those negatives with this 1 manganese. So this one has to be +4. We have no other choice. PCl5. Okay. Now, we didn't have a rule. In fact, this slide set is missing a rule. Let's see, how far did we go? Rule 7? Yeah, rule 7. We need a rule 8. Okay, rule 8. Rule 8. Fluorine. Always. -1. And if we're presented with this problem where we have a halogen like fluorine and we have some other element, non-halogen, we start with a more electronegative. Now, what can we say about chlorine? Well, first of all, phosphorus and chlorine together make a covalent compound. So we have to make a choice. We have no idea what phosphorus is in a covalent compound. But we can say that chlorine is more than likely, since it's more electronegative, it's going to be the negative one. And chlorine then would be -1, like fluorine. The halogens would be that way. Okay, so if that's -5, this has to be +5. If we can't make that assumption, then we're stuck, right? We can't calculate what phosphorus is. We don't know what chlorine is, right? Like I said, this is a bookkeeping team. We just need to have some way to track the electrons. And then SF4, I just gave you a rule for fluorine, so that's no problem. This is -1, that means -4 total. That's a +4. Sulfur has to be +4. All right. Okay, now we introduced all these rules because we needed a way to assign oxidation numbers and track the movement of electrons. So now that we can determine the oxidation number for all the elements in the reactants and products, then we can compare elements from one side and the other and see if they have lost or gained electrons. That's what we're aiming at. Okay, here's a good one. Calcium and chlorine in this vessel have been ignited. You have to add a little bit of energy, needs an ignition source, but once you get them started, then the reaction is extremely violent. And if we take our rules and say calcium is going to be 0 oxidation state, chlorine, Cl2, is its most common, most stable state at standard temperature and pressure, it'll be 0 also. But on the other side, on the product side, let's see, from your perspective, it's over here. Calcium is an alkaline earth. It's going to be +2. And chloride is a halogen. It's going to be -1. Right? So we can show, actually, we can show that with this +2 and this -1, I like to draw tie lines. So calcium did what? How did it go from 0 to +2? Remember, you cannot change the positive charges because that means protons. If you change the protons, you're changing the element. So we have to explain this change in terms of electrons. And that means redox definitions. So from 0 to +2, there was a loss of 2 electrons for each calcium. Okay? How about chlorine? Chlorine went from 0 to -1. That means it had a gain of 1 electron per chlorine, and we have 2 chlorines. 2 chlorines equals 2 electrons. And here we have times 1 calcium equals 2 electrons. All right. Now, I may be jumping ahead a little bit, but this is a perfect example. This is a loss. Oxidation is loss. So calcium is oxidized. Chlorine gains, so it is reduced. Oil rig, oxidation is loss, reduction is gain. And you'll also notice that they always occur together, right? I probably got another slide on this one. They always occur together, oxidation and reduction. They cannot occur separately. And the number of electrons, the total number of electrons transferred must be equal in both processes, right? 2 electrons, 2 electrons. Keep that in mind when we discuss subsequent. Okay. We're going to play a oxidation number game again. H2SO4, we want to know the oxidation number of sulfur. H2SO4. We can approach this one of 2 ways. You can do the whole neutral compound. We'll do that one first. Hydrogen is +1. Right, so that's +2 total. Oxygen's -2, so that's -8 total. That's -6, right? Add them together. That means sulfur must balance that -6 because this is a neutral compound. There you go. The other way you can do it, we know that sulfate is a polyatomic ion with a 2- charge. So if this one's -2, -8 total, and we want to hold 2 of those out, that means we only have to balance a -6. So it's +6. Now, either way works. Okay? Oh. So let me see. Do I have an example coming up after this one? Oh, I need an example to satisfy these. Okay. Let me think of a different one. Let's burn propane. No, let's burn methane. That'd be easier. Let's burn methane. Methane gas plus oxygen gas yields, and the complete combustion in this reaction always produces carbon dioxide and water. Okay. Now we know it's an oxidation reduction reaction because there's an element here. Well, it's a combustion reaction. Plus there's an element here. It's in compounds over here. But let's do the oxidation number. That one's 0. All right, that's element in its most stable form. This one is +1, +4 total. That means -4 for carbon. Over here we have -2, -4, +4 for carbon. Over here, -2, +1. Okay, so what's happened? Let me remove these so I can draw tie lines. How about the carbon? Okay. Carbon has gone from here to here, and it has done what? It has lost electrons. It's gone from a negative to a positive. So how many electrons is that? Well, to go from -4 to 0 is 4 electrons. And go to 0 to +4 is another 4 electrons. So we have lost 8 electrons per carbon. Let's see, are we balanced yet? That's the good question. I didn't balance it, did I? Okay, carbon, carbon, 4 hydrogens. 4 hydrogens, that means 2 plus 2 oxygens, 4. We need a 2 here. Now we're balanced. Okay. And there's only 1 carbon times 1 carbon equals 8 electrons total. All right. What is this? Oxidation is loss. This is oxidized. Okay. How about oxygen? Oxygen goes 2 places. They're both -2. Right? So we have gain. How many electrons? Each one gain 2 electrons. 2 electrons per oxygen. How many oxygens are there? Well, there are 4 times 4 equals 8 electrons. Okay? And that means that oxygen was reduced. Okay? Now, the oxidized species, this methane or carbon in the methane, since it was oxidized, it caused the reduction of oxygen. In other words, it transferred its electrons to oxygen to reduce it. So that means this oxidized species is the reducing agent. And for the same reasons, this reduced species, oxygen, is the oxidizing agent. Okay? New terminology. And there's our oil rig again. Okay, this is just a summary of terms. And like I said before, oxidation and reduction always occur together. They never occur separately. This is the author of your book thinks this is helpful. When something is oxidized, when it's oxidized, the oxidation number increases. In this case, it went from -4 to +4. And when something is reduced, its oxidation number decreases. It goes more negative, 0 to -2. So, yeah, I can't argue with that. I mean, it's no more helpful than actually learning how to do this, but in case you ever see it again, that's what it means. All right. So let's clean this up. And the question here for this reaction, which is what type of reaction? Let's see, 2 of these, and we need 2 silvers and that. All right, this is a single replacement or a displacement reaction. And we know by our rule of thumb that this element here is 0. And when it comes over here, it's in a compound. That means we do have a redox reaction. What we need to do is determine which one's oxidized and which one's reduced. All right. Copper goes from 0 to what? Well, NO3 is a polyatomic ion with a -1 charge. So this is 2 minuses. That means this has to be +2. And the nitrates don't change. Right? Nitrate on this side, nitrate on that side. So we don't have to deal with the nitrates as oxidized or reduced. Copper does something. Silver ends up 0, but what does it start over here? Well, if that's -1, this one has to be +1. So what do we got going here? This copper is oxidized. And this silver goes from +1 to 0. It's reduced. Okay. So that makes this copper the reducing agent. And that makes this silver or silver nitrate, it's interchangeable. Silver or silver nitrate compound is the oxidizing agent. Okay, so which one of these fits? Well, copper is oxidized. Yes. Silver is not oxidized. So it's either A or B. And copper is the reducing agent. Yes. All right, so A would be the best answer. All right. Another concept check. Which of the following are oxidation reduction reactions, and identify the oxidizing agent and the reducing agent? All right. So let me see. Are we going to? We're not. All right. So zinc and hydrochloric acid. Produces, and this I believe is 2 aqueous and hydrogen gas. And we need a 2 over here. Okay, so this is an oxidation state of 0. This is an oxidation state of 0. This is a -1, this is a +1. This is a -1, this is a +2. So, is this an oxidation reduction reaction? Yeah, we went from 0 here to +2 there. Right? And hydrogen went from +1 to 0. So yeah, this is definitely an oxidation reduction reaction. Okay. So I think that's identified, yes. And while we're at it, which is the oxidizing agent, which is the reducing agent? Well, the oxidizing agent is the one that's reduced. So hydrogen went from +1 to 0. This is the oxidizing agent because it was reduced. That means this must be the reducing agent because it was oxidized. Okay. How about the next one? I may not have to put this one on the board. So what's the oxidation number for, I guess I better, if I'm going to talk about it. CR207, 2 minus, plus 2OH minus yields 2CR04, 2 minus, plus water. Okay. The oxidation, let's see, the number for oxygen is -2, -1. That gives us a minus here. That's good. This is 7 times -2 is -14. And we have to hold 2 out, -12. So we need +12 over here. It means each one is +6. Okay, look on this side. -2 for oxygen times 8 is -8. Hold out 2. 1 is +6. This is a -2 and a +1. Excuse me. +1. So you can see at a glance that there were no changes in oxidation number for any of these elements. That means B is not an oxidation reduction reaction. All right. Now, I need room for the next one, so I'm going to erase these and talk about that last example. Let's see, copper 1 chloride. 2, copper 1 chloride. It's in an aqueous solution. Right? And it yields copper 2 chloride plus copper metal. All right. What's strange about this one is you got copper in 2 different places over here. So let's do the oxidation numbers. Right, we have to say chlorine is a halogen, is -1. That means this copper is +1. This one's a -1, that means this copper is a +2. This one is a 0. So what happened? Well, notice we've got 2 coppers here, and we've got a copper there and a copper there. So one of these coppers went one direction and the other copper went the other direction. So we're going to draw a tie line from this one to this one. And this one was oxidized, right? It lost electrons, which means it is the reducing agent. And it also went down here like this. This one was reduced. We add electrons to it. That means it's the oxidizing agent. Right? So copper 1 chloride is both the oxidizing agent and the reducing agent. Okay. This reaction has a special name, and it's called a disproportionation reaction. Now, it's not one of these units didn't go both directions. One unit went one direction, the other unit went the other direction. All right, so you still have to have two of these reacting with one another. It's just in our balanced equation, it looks like this one split its personality and went both directions, but it didn't. All right, let's talk about a theory that explains chemical reactions as best we can. And the theory that works the best currently is known as the collision theory. The collision theory of chemical reactions. And like I've said before, if you take the name and look at what the name is saying, then you can get a lot of information from it, right? Well, it's a theory, right? It's not a law, it's a theory. It tries to explain why reactions occur. It's a collision theory. So there has to be collisions, there have to be impacts among the reactants. That's the first thing. You have to have collisions. Number one. Collisions are required. Two reactants that don't collide will not react. And then you have to have a minimum collision energy. A combined energy of the collision must exceed a certain amount, and it varies depending on the reaction. This is called the activation energy, often abbreviated E sub A. And then the last one is orientation is essential. What we're saying is that if two reactants collide with enough energy, but they're oriented improperly. In other words, the reaction is going to occur at a certain place on this molecule and a certain place on this molecule. And if they collide opposite, then no reaction. They have to be oriented correctly to form what we call an intermediate or an activated complex. Okay, these reactants can be molecules, they can be ions, they can be atoms. They have to come into contact with one another in order for any chemical change to occur. And they need that minimum amount of energy. This is kinetic energy. They have to be moving, a mass moving at a certain velocity equals kinetic energy. Right? Has to have mass, has to move at a certain velocity. And that energy of both the combined energy in collision has to be enough to exceed the activation energy. And then the orientation is required. Reaction rates vary all over the place. Some are lightning fast and some take forever. Right, so there's a whole range of speeds for chemical reactions. Here's an example showing orientation of the molecules. In the first one, the orientation is proper for nitrogen dioxide and carbon monoxide are oriented properly so that the one oxygen on the nitrogen dioxide now is transferred over to the carbon. We have carbon dioxide now and nitrogen monoxide. But the others, the first one, the oxygens hit each other, no reaction. The oxygen hits the nitrogen, no reaction. The carbon hits the nitrogen, no reaction. Okay, three factors that are necessary for chemical reaction to occur: collisions, activation energy, orientation. All right. We're going to leave the theory now for a little while. Talk about the heat of chemical reactions. At two types. Now, I'll start by saying there are very few reactions that do not either consume heat or emit heat. Notice they don't release energy or absorb energy in the reaction. Most reactions do one or the other. But there are a few examples where the change in energy before and after a reaction is zero. But for the most part, your reaction is either going to give up energy, that means it'll get hot, or it's going to absorb energy from its surroundings, and that will be sensed as a decrease in temperature or cooling. When we release energy, we call that exothermic. Right? Thermic means heat, and exo means out of. Right? So heat is being released from the reaction. Perfect example is our Bunsen burners. Right? When we needed to heat something with a Bunsen burner, we burned methane gas, natural gas, and the exothermic reaction gave us enough heat to perform whatever process in the lab that we needed. Now, when this occurs, think of reactants yields products. Okay? The reactants have a certain amount of energy, combined energy, in all of their bonds and all of their physical condition. All right, so we'll say that's energy of the reactants. And then the products also have a combined energy in their bonds and their physical conditions. Okay? If the combined energy of the products is less than the combined energy of the reactants, we get an exothermic reaction. Exothermic. Now, I find it convenient to say, okay, let's make heat a component in the equation. So if it's exothermic and this one is less than that one, where did the heat go? Well, now the heat is over here. Right? That delta H is a fancy term called enthalpy, right? But it means heat. So this one plus this one equals that one, right? That's true. You can't create matter. You can't destroy matter. You can't create energy. You can't destroy energy. It's got to go somewhere. So if this one is greater than that one, then this is the difference. That's for an exothermic reaction. Another way to look at it is a diagram. This is energy. This is energy. And we have reactants at all the energy here. Reactants are here. Okay. This would be E sub R. And then when they collide, that energy is converted into, that energy is used to break bonds and start to reform new ones. So it's breaking bonds as we go here. And this is progress of the reaction. Progress of the collision. Okay, so it's starting to break bonds, and it gets to here, This is the activation energy level. Now we're at the other side. Now we're starting to reform new bonds. And these new bonds take us down to a lower energy level. So we have energy of products. Okay, so the difference between this one and this one is activation energy. And the difference between this one and this one is the heat. In this case, the heat that's released, right? Because you got lower energy here than you do here. That energy is released. This is exothermic. And remember what I've said in the past. If you have an initial measurement and a final measurement, the difference is the final minus the initial. So if we say this one is at a certain value minus this one, and this one's bigger than that one, what's the value going to be? It's going to be negative. So we can put values in energy units. We can assign values in energy units to a chemical reaction. And if the sign is negative, we know that it's exothermic. We go turn it around. If we go the other direction, say, let's see. Yeah, let's just erase it all. If we start out with energy of the reactants, and we have a collision. Oops, sorry, went the wrong direction. Energy of the reactants, and we have a collision. And these are the products. Energy of the reactants, energy of the products. We still have an activation energy here. Right. And the difference here is the enthalpy of the reaction. And if we take this one minus that one, this one's less than that one. So when we subtract the two, we get a positive value. So this endothermic reaction, endo means into, heat. And if we have reactants, yield products, where would the energy be placed? It would be on this side, right? Because the energy of the product is greater than the energy of the reactants. Like that. Okay. An example of this is photosynthesis. Right? Plants take carbon dioxide and water and combine them and make carbohydrates. That's a starting point. And the carbon dioxide and water are at a lower energy state than the products. Carbohydrates start out as simple sugars, right? Like glucose, fructose, those things. And it needs an input of energy. Energy has to be added to the system. And this, in the case of photosynthesis, is sunlight. Sunlight. There we go. Okay. And there's what it looks like. Which one of these is correct? During an exothermic reaction, the average energy of the products is higher than the average energy of the reactants. No. And exothermic means that the products are lower energy because we have released some of that energy from the reactants. During an endothermic, the average energy of the products is lower than the average energy of the, okay, they've got A and B are backwards, right? So how about C? During an exothermic reaction, the average energy of the products is lower than the reactants. That is true. C is the best answer. All right. So let's talk about this, what we've discussed so far. We've actually combined a discussion. And with that energy diagram, there are various parts of it. The energy of the reactants, energy of the products, those are before and after. And what happens in between, in some types of study, doesn't matter. You just want to know what the beginning state is and the ending state. And what happens in between is immaterial to your studies. But the part in between where we get activation energy over the top before it gets to products, that part of the reaction curve describes how fast the reaction will go. The chemical reaction rate. All right. So let me just draw it again. Progress and energy. So if we want, say, an exothermic reaction, like this, like that, down there like that, okay? And this is activation energy. This is reactants. This is products. Okay? There's a whole branch of chemistry and physics called thermodynamics. And that branch is concerned only with this part and this part. They don't care what happens in between. Well, maybe they care, but it's not as important. Then when we go to chemical reaction rates, we're in a different branch of science called kinetics. And this determines how fast the reaction will go. It's how much reactant is consumed in a given time period. And it depends on the reaction. It could be so much a molar change in concentration per second, or per minute, or per hour, or per day. Right? Some reactions are very slow. So what determines the reaction rate? Okay. It all goes back to, well, the first factor is a physical factor. The physical nature of the reactants. Let me see. Let me check myself. Yes, we're going to have a detailed discussion in subsequent slides. So I'm just going to name them first. The physical state, the concentration of reactants has a bearing. Temperature also has a bearing, and whether or not there are catalysts involved. So we got to define our terms in here also. All right, first one, physical nature. What's the physical state? Solid, liquid, or gas? And if we have a solid, particle size. If the reaction rate is generally faster between liquid state reactants than with solid state reactants. And the fastest are gaseous state reactants. The reason being that you have more collisions. Right? If you have a solid and a solid, or a solid and a liquid, where can they have collisions? They can only have collisions on the surface of the solid. Right? So that limits the number of collisions that can produce a reaction. That means it's going to be slower. If you mix two liquids together, then that could be useful, right? If they are both miscible with one another, then you can get the reactants in the same vicinity, but on their way to the collision, they might hit somebody else and not produce a reaction. So you've got a lot of dud collisions in liquids. In gases, the gas molecules, the atoms molecules are very far apart, and they make fewer intermediate collisions without producing reactions. So when they collide, as long as they have the proper orientation, you're going to get a reaction. So we tend to have, let's see, the state as an influence. The rate of gas is greater than liquid and greater than solid, as a general rule. And then you can speed up the solid reaction if the particle size is smaller, because then you have more surface area. That's why in coal mines, proper ventilation is absolutely essential. You have two possibilities for explosions in a mine. One is gas. You hit a gas pocket, the gas is released, mixes with the air, and all it needs is a spark, and you're in trouble. The other is coal dust. So when you start chipping away at the coal, you produce fine particles. And if you don't sweep them away, they accumulate. And since they're very, very small, and the oxygen in the air now has lots of surface area, you can get a reaction going fast enough that it is essentially an explosion. Okay. So that's the physical nature of the reactants. Reactant concentrations. So as the concentration of your reactants goes up, the rate of the reaction increases also. Why? Based on the collision model. Hey, I'm teaching to myself today.
I just want to say hi.
Okay. So according to the collision model, if you have more collisions, the reaction rate should go up, because the probability of having the proper orientation and energy is based upon how many collisions you have. So maybe only 1% of the collisions have the proper energy and the orientation to produce a reaction. Well, 1% of 1 molar is a value. 1% of 10 molar is 10 times that. So you increase the concentration, you increase the reaction rate. Temperature. The temperature effect is very easy to explain. Temperature is a measure of kinetic energy. Temperature is proportional to the kinetic energy of the molecules. So as the temperature increases, the kinetic energy of all the molecules increases, the average kinetic energy proportional to the average kinetic energy. So what effect does that have? Well, it means that more of the collisions will meet or exceed the activation energy. If those collisions have enough energy and the orientation is a factor that's already fixed for that particular reaction, then all you have to do is increase the activation energy, and you're more likely to get a reaction because the energy exceeds the activation energy. And that will increase the speed of the reaction. All right, and the last one is catalysts. So what's a catalyst? A catalyst, by definition, is a substance that participates in the reaction, but is not, it goes in one end and comes out the other unchanged. It does participate in the reaction, right? It does combine with the reactants in some way, But at the other side, when the reaction is complete, it is spit out unchanged. It looks like it's unchanged. And it also increases the reaction rate. Right? If it decreases the reaction rate, it's not a catalyst. Right? It's an inhibitor. So we're talking about catalysts. They increase the reaction rate. So how do they do it? Well, go back to this grade. This is where we're talking about kinetics. Reaction rates. So what does a catalyst do? What it does is it provides the reaction with an alternate pathway of lower energy. In other words, on this diagram, that would be the activation energy for a catalyst. It decreases the amount of energy required for the reaction to proceed. So what does that mean? Well, if you're at the same temperature as before, and all the molecules have the same average kinetic energy, and they're all colliding, if they have a catalyst, then the catalyst offers an alternate pathway that requires less energy. Right? You've already got the energy. If you need less of it, that means more of the reactants are going to produce products. Now, the catalyst doesn't change what happens to the reactants. It still produces the same products. Right? They just do it faster. Now, there's a difference between inorganic catalysts and organic catalysts. Organic catalysts are called enzymes, and our bodies are just chock full of organic catalysts, these enzymes. They allow reactions to proceed inside our cells at a rate that's biologically significant. Many of the reactions that occur in our bodies, if we didn't have these enzymes, would not occur fast enough for us to actually live. That's one difference between inorganic and organic catalysts. Also, inorganic catalysts, like for instance, the Haber-Bosch process, where you have nitrogen plus hydrogen yields ammonia. Right? So I need, let's see, 2 here and 3 there. This proceeds at a certain rate, and we want to speed it up. All right, so what Haber did was, well, actually, what first thing he did was increase the temperature and pressure. All right, he increased the number of collisions and the energy of the collisions. So he approached it here and here. Right, pressure for gases is concentration, and temperature is kinetic energy. The problem is, he found that the equilibrium position for the reaction when you increase the temperature is over here. So what he needed to do was speed up the reaction, go in this direction. And he used iron, very finely divided iron, as his catalyst. This is an inorganic catalyst. Okay, so what did that do? Well, in effect, it increased the rate of the reaction that way, but inorganic catalysts are not selective as far as the direction of the reaction, right? They could go to the right or to the left at increased speed. So Haber has increased this, increased that, used a catalyst. Now what does he do to make the reaction continue to the right? Well, he cycles the gases through a condenser. He cools them down. Ammonia will condense into a liquid at a higher temperature than nitrogen or hydrogen. So he extracted the ammonia and then sent the gases back into the reactor and just kept cycling like that. Right, so he's continually removing product. And we'll talk about that later when we get into Le Chatelier's principle. All right, what do enzymes do? Enzymes work a little bit differently than inorganic catalysts, and they are very specific for reactions, most of them. catalyze reactions in only one direction. So if you have a catalyst going this direction, then you need another catalyst to go the other direction. Now, there are some exceptions to that, right? One in particular, you look it up, it's called Rubisco. That's abbreviation for the catalyst. And it has to do with photosynthesis. But in general, enzymes go one direction, and then you need another one to go the other direction. And they are also controllable. Right? Most enzymes can be induced, they can be activated and deactivated. So those are major differences between inorganic and organic catalysts. And this is an expression of what the catalyst actually does. It decreases the activation energy for that reaction. And that allows the reaction to proceed much faster. Right? It increases the rate, catalysts increase the rate of reaction by decreasing the activation energy. That's a simple statement, and it is true. Now, when we talk about chemical equilibrium, now we're getting into, for this diagram, we're talking about this one and this side over here. Okay, I mentioned thermodynamics, but we're going to narrow it down to equilibrium. What do we mean by equilibrium? Well, when you have a, let's see, I better erase some things here. When you have this reaction right here, I mentioned that it can go forwards and backwards. And that's true of most reactions. There are some that go so far to one side that they're essentially complete. But most reactions are in a state of equilibrium between you have some reactants and you have some products in the reaction mixture at the same time. What we're looking at is the rate of the reaction in one direction versus the rate in the reverse direction. So this would be the rate in the forward direction. This would be the rate in the reverse direction. Okay? Now, when those rates are equal, you have a state of chemical equilibrium. Now, what do we see from the outside? What we see from the outside is that there's no further change. The concentration of reactants and the concentration of products appear to be static. Right? That's what we observe. But at the microscopic level, right, if we could get down small enough to watch it, the activity would be furious, going this direction and that direction, both at the same time. And when those rates are equal, when this rate forward equals the rate reverse, that's equilibrium. All right. Now, it's important to note that the concentrations don't have to be half and half. Right? Depending on the reaction, you could have most of them over here, or you could have most of it over here. The equilibrium is based upon the rate. At that point, the forward rate and the reverse rate are equal. And depending on the reaction, you could have an accumulation of product, or you could still have a lot of reactant and very little product. And this is a way to look at hydrogen plus iodine yields hydrogen iodide. And the initially, right, the rate of the forward reaction starts to decrease. Why? Because you're decreasing the concentration of the reactants. So the rate decreases. But as you produce product, then the product is returning and the reverse reaction is starting to increase. When they meet, the reaction rates are equal now. That's equilibrium. Now, if we draw the diagram in terms of concentration, we find that for this reaction, the concentration of hydrogen iodide is 0 at the very beginning, right? Right down here, 0. Oops, sorry. There we go. But its concentration steadily increases. And the concentration of hydrogen gas and iodine decreases until they appear to be stable. Their concentrations don't change anymore. Now, what do we mean by a reversible chemical reaction? Well, at the microscopic level, all reactions are reversible, right? It's the extent of that reversibility that matters. But all reactions are reversible in some sense. The reverse rate may be slow, or the forward rate may be fast. If the reverse rate is very slow, then it appears that the reaction is irreversible, and you go all the way to products. Okay? A state of chemical equilibrium is reached when the concentration of all reactants and all products remain constant, and a reversible reaction is one in which the conversion of reactants to products and the conversion of products to reactants occur simultaneously. Concept check. Okay, we're leading into Le Chatelier's principle. So if we have this chemical reaction, water plus carbon monoxide yields hydrogen plus carbon dioxide. What happens if you add water to the flask? Right, you got H2O and carbon monoxide yields carbon dioxide, hydrogen, excuse me. Let me keep them in proper order. They put hydrogen next plus carbon dioxide. Okay. What happens if they're at equilibrium, right? The forward rate and the reverse rate are equal now. Now what happens if you add more water? You've changed the concentration of water, increased the concentration of water. Now you have the potential for more collisions with the other reactant, and the forward rate increases. And it increases until you produce enough of the product so that the reverse rate increases. And once they're balanced again, you reach equilibrium. But how do the concentrations behave? The concentrations at equilibrium now are greater over here and slightly greater here because you don't use all of it up. And this will be reduced. How about adding more hydrogen? Well, if you add more hydrogen, you've got the reverse situation. Now the reverse reaction is increased until you get enough reactant here to balance the forward reaction, and then equilibrium is reestablished. You can also, not just by adding, you can subtract. Say we subtracted carbon dioxide, we removed it somehow. Then this reverse reaction would be decreased until this forward reaction produced enough to replace it, and now the reverse reaction and the forward reaction balance again. Now, there's when we write an expression like this, we can also attach a mathematical expression for any equation. It's called the law of mass action, and it produces an equilibrium constant. Now, this is constant as long as the temperature stays the same. If you change the temperature, the constant will change. And it looks like this. I need to change that slide. I like it better if you do this. All right. If you have reactants with their coefficients and in equilibrium with products and their coefficients, then we can write an equilibrium constant this way. You need the concentration of the products, the product of the products' concentrations, like this, right, multiplied, and each one is raised to the power of its coefficient. So this will be raised to the C power, this will be raised to the D power, and then in the denominator, you put the reactants. Right? That gives you an equilibrium value, an equilibrium constant. Let's see. Okay. We use square brackets for molar concentration. So we would express each of the reactants and products in molarity. We can also write, I'm not sure if I'm going to do this one or not, but I'm going to do it here anyway. We can write a case of P if we use partial pressures. If all of them are gases, say all these guys are gases, we can measure the partial pressures of each one. And we can do the pressure of C to the C power and the pressure of D, the D power, divided by the pressure of A to the A power and the pressure of B, the B power. And that would also give us an equilibrium constant. It would be different than this one. If you expressed it in molarity, you get a different value than if you express it in atmospheres. But the reactants are always placed in the numerator, the products are always in the numerator, the reactants in the denominator. Now this KEQ is a general expression and usually means molarity, but there are other subscripts for K, right? Besides the KP, we could have a K, there's one for KW, which is water. Water reacts with itself. Ka for acids. Kb for bases. All right, so the subscript has a meaning. The other thing we do is if any of the reactants or products are either solids or pure liquids, they are not placed in the expression. They're left out. Why? Because pure liquids and solids don't change concentration. We need reactants and products that change concentration. So they're either gases or they're in solution. And they're never included in the calculation. Okay, temperature dependence of equilibrium constants. It depends, right? Temperature dependence depends. It depends on whether the reaction is exothermic or endothermic. Right? If the reaction is exothermic, you have that first example, reactants yield products plus heat. What happens if you introduce heat as an element either in the reactants or product side? What happens if it's in the product side and you increase the temperature? You're adding heat. You're adding that delta H to one side. So the reaction then is favored in the reverse direction. Right? So what does that mean? Well, if the KEQ is equal to products divided by reactants, right? And we have the concentration values and the powers and all that. Well, what happens to the KEQ if it's exothermic and you increase the temperature? Then you favor reactants, right? You favor reactants. That makes the reactants bigger, the product smaller, and the KEQ decreases. The other possibility is if the reaction is endothermic. Then if you increase the temperature and you add heat to the reactant side, you increase the reaction to the right and you produce more product. So you increase the product and you decrease the reactants. In that case, the KEQ increases. Okay. We can also say that if we're comparing two different reactions and we have a KEQ for each one, then if the KEQ is large, much, much greater than 1, that means this value here is large and this is small. So with a large K, you are favoring products. On the other hand, if you've got a small K, much, much less than 1, then you have very small number of products and large reactants. You're favoring the reactant side of the equation. Those are generalities that we can draw from the K value itself. Now, I'm going to leave that up there. The K is a constant, and it is a constant as long as the temperature doesn't change. But if we start the reaction with only reactants, we get a certain concentration of reactants left and some product. But if we start with some reactants and some products already and let them react, you get a different concentration of reactants and products. But they're still at equilibrium. And those concentrations, if we place them into the formula, will give us exactly the same K. Right? So those differences in concentration signify an equilibrium position. An equilibrium position is not an equilibrium constant. The position eventually will allow us to calculate the constant, but the position might be different depending on your starting conditions. All right, so this came straight out of your book. What's the equilibrium constant expression for the reaction H2I2 2HI? All right. Assume no solids or pure liquids. Okay, in that case, then we would put HI to the second power in the numerator. And that would be D would probably look the best. And then the H2 and the I2 in the denominator. All right, so that would be our equilibrium expression. Now, what we've been leading up to is Le Chatelier's principle. Le Chatelier was a Frenchman working toward I think he was toward the end of the 19th century, if I'm not mistaken. And he noticed that a system that was in equilibrium could undergo a stress. We could place the system under stress. And that, depending on the reaction, stress could manifest itself in different ways. We'll discuss those in a minute. But when you put an equilibrium system under stress, it will respond. And it will respond in such a way as to reduce the magnitude of the stress. Right? So what are the possible stresses that we can put on a equilibrium system? One could be change the concentration. Change the concentration of one or more of the reactants and products. And that stress will cause the reaction to shift in such a way as to mitigate the addition or subtraction of a reactant or product. That's the easiest one to understand. And we discussed it a little earlier when we added water to a reaction or we added hydrogen to the reaction. Which way did it shift? Now, when you say a reaction shifts to the right or the left, right, we have, say, A plus B yields C plus D. If we add A, we're going to shift to the right. Okay? That makes sense because we have our balanced equation here to reference. We can say it shifts to the right when we add A, or when we add B, or when we subtract C or subtract D, it will shift to the right. If we don't have that equation and we say right and left, means nothing. Without a balanced equation to reference, right and left have no meaning. They are not valid expressions for describing a Le Chatelier's principle. All right, concentration changes. I mentioned that one already. What happens as far as Le Chatelier is concerned is if you have a system at equilibrium and you stress it by changing concentration, then you get a shift in equilibrium position. But once it reaches equilibrium, the constant, of course, is constant. All right. I'm not going to spend time on this slide because it says the same thing I've been saying, just in pictures. Another way to affect the equilibrium, temperature. Oops. Wrong place. Change the temperature. Okay, and we discussed how the temperature affects equilibrium. Right? If we have an exothermic reaction and we increase the temperature, we're adding to this side, shifts the reaction to the left. If we have an endothermic reaction, then we're adding heat to this side and it shifts the equilibrium to the right. Now, it does that because changing the temperature changes the constant. Not just the equilibrium position, but it changes the constant. And if you have heat on this side and you add heat to it, then you're increasing this rate, but you're not increasing the reverse rate. So it shifts the reaction this way. It also changes the K. Here's an example, right? If this reaction, the effect of temperature, if we decrease the temperature, we're shifting the reaction to the right. So decreasing the temperature means that this is an exothermic reaction and we're removing heat, right? We're cooling it down. We're going from blue to pink by removing heat and shifting the reaction to the right. Now, if your reactants and products are all gases, then we can affect the equilibrium by changing the pressure of the gas. Now, you can change pressure in different ways. You can add more reactant into the same volume and increase the pressure, but we've already discussed that one in concentration. So what we're going to do here to change pressure is change the volume, right? Use Boyle's law. If you decrease the volume, you increase the pressure, all right? So if we increase the pressure, if these are all gases, and we increase the pressure, how is the system going to respond? The only way the system can relieve that pressure is to produce fewer moles. Okay, produce fewer moles of gas, total gas, in the reaction vessel. So our example here is the Haber process again. So let's do this one. 3, right? Yeah, 3 gas in equilibrium and 2 ammonias. This is an exothermic process. But if we increase the pressure, which way will it shift? To determine that, you find out from the gases, what are the total number of moles here? 1 plus 1 plus 3 equals 4 moles. 4 moles of gas in the stoichiometry. On this side, you have 2 moles. So if you increase the pressure, the response is going to be toward fewer moles. So increasing the pressure shifts to the right. If you have equal moles on either side of the gas, then changing the pressure by decreasing the volume will have no effect. Right? There's no response of the system to that change. Or if you add an inert gas changes the pressure, but it's not part of any of the reactants or products. So it has no effect on the reaction. And then if you add a catalyst, what does that do to the equilibrium? It changes the rate of the reaction in both directions. It changes the forward and the reverse, right? So if we add iron in here, it changes the forward and reverse, but it doesn't change the equilibrium at all. So catalysts have no effect on equilibrium. All right. Yeah, that was number 4. Catalyst. No effect. It just reaches equilibrium quicker. What factors affect Le Chatelier's principle? Affect equilibrium? Concentration, temperature, pressure. Okay, so we've got a concept. We've probably got 2 concept questions here at the end of this chapter. And then, yeah, that's good. All right, so let's make some room in case we need it. A breathalyzer. I've never breathed into a breathalyzer. They do it sometimes. Just random stops. They have roadblocks set up, state police or local police, and they make you blow into this thing to see if you're driving intoxicated. This is one of the reactions that is used in the device to determine whether or not, to determine your blood alcohol level. So potassium dichromate reacts with the ethanol, CH3CH2OH is ethanol, reacts with ethanol that's in your breath, also with sulfuric acid. Those 3 combine and they produce chromium 3 sulfate plus potassium sulfate plus acetic acid plus water. And let's see, what do they measure? I think they measure the acetic acid produced. And the stoichiometry there is related to how much alcohol you had in your breath at the time, and how much is in your breath is correlated with how much is in your bloodstream. Okay, so in this reaction, which is undergoing reduction and which one is undergoing oxidation. All right, so we would have to, let's see, am I going to, yeah, I'm animated, I think. There we go. So we determined the oxidation state for chromium earlier in this compound at +6. And in this compound, if we go through the procedure and determine the oxidation state of chromium in the product, it's +3. So that means chromium was reduced. It went from +6 to +3. Okay. That carbon is -1. That carbon is 3+. All right. The CH3 carbon didn't change. CH3 in the ethanol, CH3 in the acetic acid did not change. So we're focusing on the carbon attached to the oxygens. All right. So the chromium 6+ is reduced to chromium 3+, while the carbon in ethanol oxidizes to the carbon in acetic acid. So which one is the oxidizing agent? Well, of course, the potassium dichromate is, and the reducing agent is ethanol. Okay? All right, so that's the end of that chapter.